Hello, so today we are going to look at backtracking and how we can solve problem using backtracking. So what I will be trying to do here is devise kind of a template or a way to think about solving these kinds of problems. And so first let's just look at what backtracking is. So it's just a way that allows us to iterate through all possible configurations of all possible configurations of some search space, right? So, for example, let's take examples here. So, for example, when we want to find all permutations of something, of an array, of a string, then that means we want to find all the permutations of something. So that's all the possible configurations or all the possible orderings of that list, for example, of elements. And another example we can take is all subsets of some sets. So again, you can see the format is pretty similar. It's all possible configuration of something, for example, here it's all the possible ways to build a collection, a smaller collection out of a bigger set or a bigger collection. There are other more complex problems, like for example, enumerating all spanning trees, or spanning trees of a graph, all of them. Or for example, listing or enumerating all paths between two vertices. And so you can see all these examples fits into this description of iterating through all possible configurations in some space. And so one thing we can say about these problems is that they all have in common something which is, apart from the format here, they all have in common that we must generate each one possible configuration exactly once. So we don't want to generate the same configuration multiple times. Like for example, for permutation, we don't want to, if we want to permute A, B, C, D, we want to get A, C, D, B, A, D, B, C. We don't want to get this 2 times, for example. Same thing with subsets. If we want the subsets of let's say 1, 2, 3, we want to get 1, we want to get 2, maybe 1, 2, like this. But we don't want to get 1, 2, 2 times, right? And so that's one of the characteristics, is to generate each possible configuration exactly once. Exactly once. The other characteristics that we want is that we don't, so exactly once, which means we don't want repetitions, but we also don't want to have missing configurations. We don't want to, for example, if we have same thing, the subsets example, we don't want to have, for example, this one not appear in the set of solutions, right? So that's another thing. And for enumerating all spanning trees, we don't want to have like one spanning tree missing from our set of solutions. And so to do this here, I'm going to just give some template of solving these types of problems. And so the first thing we are going to do is model these kind of problems in a similar way, so that we can have a generic template for coding a solution to these problems. And so what we want to do is we want to model the solution. Each of these possible configuration is considered a solution as a vector that we will call, which is an array list in Python. It can be an array in other languages, but I'm just going to call it with the generic term vector, and let's call that A, and that's just the elements in one solution. And so for a permutation of A, B, C, D, that solution vector can be A, B, C, D. It can be for another permutation, something like this. For a subset, it can be for a subset for 1, 2, 3. That solution can be 1, 2, 3 or 1, 2. And so you get the idea. It's a possible solution. And so at each step for this vector, at each step of the backtracking algorithm, what we want to do is extend this. And so, for example, backtracking is, of course, recursive. And so at each step, we are, let's say, at k position of vector A. So, for example, for permutation of n element, let's say we have so far 3 letters from the permutation. So at that point, our k is equal to 3. And so at k position of vector A, so that would mean we would have A1, A2 until AK. And our goal at each step, basically, is to extend vector A, which is, so far it's called our partial solution. So basically extend vector A in a way that doesn't violate any constraint of the configuration that we want to generate. So that satisfies the constraint of the problem. And so what is an example of this constraint? So for example, in the permutation case again, so in permutation case, a constraint would be to not have the same element appear twice. Like if I have, let's say if I have A, B, C, D, and my partial solution already contains AC, my constraint here is to not extend my vector, so this would be my vector A. It's to not extend that with C again, right? I don't want to extend that with C again, because that means I'm violating the constraint that my permutations has to contain each element only once, right? And so here I would have to choose between B and D. And so thinking about this here, and it's recursive, and we construct this vector. At each call we extend the vector by one element. And so recursive means we need some termination condition, right? And so what is the termination condition here? So that happens when we have a full solution, basically. And so when do we have a full solution? That's when the size of vector A is equal to the length of the solution that we want, right? Let's call it n. And so, for example, in a permutation, that would be the length of the original string or the original list. And so, looking at this, if you kind of see what's happening is that at each step we generate a partial solution. The backtracking algorithm would end up constructing a tree of solutions. And so, for example, for A, B, C, D, it will pick A, B, C, D as part of the partial solution. And so the remaining element in this case would be B, C, D. The remaining elements, let me just draw this in a more clear way. So what we would have is we pick A as the first element of the vector solution, and the remaining element would be B, C, D. And then we pick B as the other element of the remaining solution. And then we pick C as the other part of, so this is the A vector, and this is what's remaining. And then you keep doing something like this, and so you can see it's a tree, and to get a single solution, it's just DFS, right? Just DFS from the top up until the leaf node, right? And so in these intermediary nodes are just partial solutions, are just values of this A vector. And so backtracking just constructs a tree of partial solutions such that each node is just a partial solution, and we have an edge from a node to another one by just extending the vector. And so if we kind of view backtracking as DFS like this, we can create our template algorithm here, which would be backtrack. Let's call it backtrack DFS because that's what we are doing here. And we need to pass A, and I'm just going to pass K, which just says where I'm at at which part of the solution am I. So for example, here I would be at K equal to 1, here K equal to 0, here K equal to 2, here K equal to 3. So it's just this, how many elements of the vector solution, of the solution vector I have generated so far. And so the base case or the termination condition is that I reached the full length of the solution, right? So that would mean, so in my permutation example, it's this, but it can be something else. So to make my algorithm generic here, I'm just going to say that A, which is the vector solution, A2 until AK so far, is a solution. If it's a solution, then just use the solution. Which using the solution here can be printing it, can be adding it to a list, whatever, can be just enumerating, so just adding a counter to get the full count. So it can be whatever. Since this is generic, you need to do whatever the solution you are looking for here. Now otherwise, if it's not a solution yet, that means we need to extend it and add another element that doesn't violate the constraint. And so to do that, since we will be advancing one step in our vector solution, we will be going down to the next node. We need to increase our K value. And then we need to compute all possible next steps that can extend this solution vector without violating any constraint. And so since we want a generic algorithm, we will just call that computing SK, such that SK is all possible next steps that don't violate the problem constraint. So for example, in the permutation case, it will be all the other letters. For example, in permuting a string, it will be all the possible letters that haven't yet appeared in the permutation. And so for A, B, C, D, when we are at K equal to 1, it's all possible letters that are not A, and so that's B, C, D. For K equal to 2, it's all possible letters that are not A, B, so it's C, D. And so we compute that. These also, we can call them like the candidates for the next solution, for the next configuration. And then we can, after that, we can just go through these. So while we still have some possible next steps, so it's not empty yet, we will pick one element of these possible next steps. So basically, we would have nodes here, so we pick one of them. So an element, that would be just an element of SK. And now since we picked it, we don't want to pick it again, right? That's one of the constraints of backtracking or of these problems, is that we want to generate each possible configuration exactly once. We don't want to repeat it. So that means we want to remove it from SK, from the possible solutions. So this just means, this here just means removing. So SK without A, that's what this means. And then after that, we want to just backtrack and continue. So once we picked one at this level, right? Once we picked one at this level here, we want to continue and pick another one on the next path, right? And so that means here we want to recurse on our backtracking. So that would mean we want to recurse, backtrack DFS, and go to the next step. But the next step, since we picked an element in our vector solution A, so now we picked the value K at AK, right? So the next step is to go pick one value for a k plus 1. And so that's why we are going to do k plus 1 here. And so this is the general solution for a backtracking problem. You can see it's a tree, and I implemented DFS. So that's naturally you can ask, well, can I use BFS? It's just a tree, and I'm just traversing it. And it's just an implicit graph that I'm doing DFS on, and the neighbors are just computing these SK values, right? And so maybe I can use BFS, and the answer is definitely yes. But it's just like, for these backtracking problems, usually the height of the tree is smaller than the width, because you have a lot of configurations, and so you have a lot of choices at each moment. And so that means that if we use BFS, we will use a lot more space, because we need to keep track of the width at each level. But the height usually in these kind of problems is a lot smaller, and so because the number of configurations is a lot longer usually than the size of one solution, and so the height is a lot smaller than the width of the backtracking tree here. And so BFS will take more time and will have more space. Will use more space, because it needs to store the entire width at each point, right? And so it can be solved with BFS, but it's just better to use DFS here. Okay, so now what we are going to do is just make this a little bit more applicable to each problem. Here it's very pseudocode, so let's just look into how we can translate this into an implementation where we can just plug things for each problem. And so it's still backtrack, right? And I'm just going to replace A with it's just an array of vector solutions, right? And then this is just the value of k, so it's just an int. Okay, let me just use Python here maybe. So A and then k, and then we would have the input, which can be anything that will help us solve the problem. It can be, for example, the original string. It can be whatever else you need to keep track of from the input that the problem gives. And what we do is we check first if it's a solution, and so we just need a procedure or a function called isSolution that, depending on the problem, checks if it's already a solution. So for the permutation, it will just check if the size is n already, and so that would be checking using whatever we can pass the entire data. We might not need to use all of it, but once we check is a solution, we can process that solution, which can be adding it to a list, can be printing it, can be counting, whatever the problem says. And then otherwise, we need to compute this SK. So I'm just going to rename this computing SK. It's just generating all possible next step. Basically, it's just constructing all the possible candidates for the next step. And so I'm just going to call that a function that gives us the candidate that we'll call construct candidates. And that would be just having input and like this, and we'll get the list of candidates. So for backtracking, at this point, it will give me A, and then it will give me B, and the rest here, and then it will give me C, and then it will give me D. So all the possible candidates at that point. And then I go through these candidates and try each one of them. And so that's this while loop here of trying every possible next step. And so that would mean for, let's call it C in candidates, I will add that to my vector solution. And then here we can have there is a generic step that we can do here, which is called make a move, or it can be called choose, which in our case here, it was just picking an element these candidates and removing, but it can be more complex in other problems. And then we can do the backtrack and recursive call for this DFS. So this would be for k+1 and the input. And then after that, we will make the move. So we made the move, which means we chose, for example, one of the possible next step and added it to some data structure. We need to remove it because for the next candidate or the next possible step, we don't want to. So for example, we picked B, right? We have only A and we picked B, and we may pick C or D. So we want to remove the choice B, because if we keep it, that means we will pick B and C. We'll make two choices at one level instead of just making one choice. And so here we will make the move, which can be also called choose. So these can be empty. We may not need to do anything. In some other problems, we may need to do some stuff, but because this is a generic solution or a generic template that we need to follow, we're just going to put in everything we need. And in some problems, we may need to terminate early because the path this candidate is taken violates the constraint, and so we just don't want to continue. We want to end right there because of some constraint in the problem, and so that we can just have a flag or a function that checks that, and if it's true, we can return and just exit the function altogether. So this is the template for solving most of the backtracking problems. So the main procedures we need is this checking if it's a solution. We process the solution. These usually are very simple to check. The usual complex thing is to construct the candidates for the next step, and then just iterate through them and do the recursive call. This sometimes here requires some thinking also, but the main thing is constructing the list of candidates for the next step. So next we'll take a look at some examples that use this template here and see how we can use it to solve the problem. Okay, so now that we've seen the template of the backtracking algorithm, let's just take as an example here, let's take for example, constructing subsets. So let's say, for example, we want to construct the subset of all elements from 1 to n. So we want all the subsets for this. How can we solve this in terms of backtracking, and then how can we use this template that we just defined to solve this problem? And so first, let's just look at this. So if we have n equal to 1, that means that we have just we have just two possible subsets, right? So we have the empty subset, and then we have the subset that contains 1, because this is basically the subset of all elements in the set 1, right? So either the empty set or the set containing only 1. For n equal to 2, we would have empty set 1, 2, 1, 2, and so basically we will have, for n equal to 2, we will have 4 subsets. And then for n equal to 3, we will have 8 subsets, and you get the idea. Every time, for every n, as we increase n, it doubles. So first we had 2, and then 4, and then we'd have 8. For n equal to 4, we would have 16 subset, and so from this you get the idea that we would have 2 to the power of n subsets. Now let's try and think about modeling this in terms of a solution vector, right? In terms of a solution vector, and then apply this template here to solve the problem. And so first, one thing to notice here is that this problem does fit the description that we had here, which is iterate through all possible configuration of some search space. So here our search space is 1 to n, and the configuration that we are looking for is a subset of that set. And so we want to iterate all the possible ones, and we want to generate each one of them. We don't want to miss anyone, and we don't want to have a duplicate or a repetition of a subset. So it does fit our requirements here. And so now, what is important in this case? So for we need to model it in terms of a vector solution. Let's call it A, and this would have A1, A2, AN. So what should A value be, right? So A can be, can be either, AI can be either true or false. Why am I doing true or false? Because for every element in 1 or n, 1 to n, we will choose either to take it or not, to include it in the subset or not, right? So either include in the subset or not. So for that, we can just have, so for example, for the empty set would be represented by the solution vector A such that all of them have false value, right? Because it contains nothing, so no element is in there. For example, for 1, if we had n equal to 4, the vector solution A would be true because that's for 1, the value is true, and then false for the value 2, false for the value 3, and false for the value 4. And so all we need to do, for example, for n equal to 2 is generate all the possible A values. So we need to also generate false, 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 and then we need to generate the case where it's still false here, but it's true here. It's false here, it's false here. And so we need to generate all the combinations of true and false, and each one of them will represent a different set. So this one would represent the set 1, this one would represent the empty set, this one would represent the set 2, and if we had, let's say, we continued and then we had a vector solution that is, let's say, false and then true, true, false. So this vector solution would be representing 2, 3. And that's a subset of the set 1, 2, 3, 4, right? And so this is the idea. So now we know what is we know what are our candidates. At each point, the candidates are either true or false. So candidates. So for this problem, we know that the candidates are true or false, right? And when do we know we have a solution? We have a solution when we chose whether to include an element or not for every element in the set. And so when the solution is just when we know that the length of A is equal to n, because that means we decided for each element whether we are taking it or not in that subset, right? And so we know the is solution, we know constructing the candidates. What is our process solution? That's another thing we need to return. So that depends on the problem. So let's just say in my problem, what I want is just print the subset. And so this here would be my process solution then, if I just want to print it. So this would be construct candidates. I would just return true and false, and its solution would be checking the length. And so now, do we need to make any move or make a move, right? In this case, we don't need to do anything because we just will say whether the value is true or false, and then that's pretty much it. We don't need to make or unmake. And so that's pretty much it. So let's code these. Let's code these 3 methods. This one. So we will need to code this one, and this one. The make and unmake, just consider them empty in this case because I won't need them. And so let's do that then. So that means for is solution, in our case here, so that function would get the array, the vector solution would get k, and then would get the input or the value n. Since we are doing a subset from 1 to n, that's the input that we got. And so the only thing we need to check if it's a solution is if the length of A is equal to n. right? Now, what about the other method that we need to define, which is process the solution? So for that one, we know that, so we will get, let's say, the vector solution, right, A, that contains true and false values here, which each represent whether the element I should be included in the subset or not. And then we would have K. So what we want to do is just go through them. We want to just print it, right? We want to just print the subset. So we are going to go through all the values, which are I in the range from 1 to K. And then we can just check if it's included in the subset, then we print it. If it's not included, we don't want to print it. It's not part of the subset. And so let's just print first the opening bracket like this. And then we can check if AI is true, which means we are choosing that element, which means pick the element. The element is picked. Then at that point we can just print AI and then maybe print just a separator here. And once we are done, close the opening bracket. And that's pretty much it for the process solution. And so to finish this plugging, defining the method that we need to plug in our template, we just need to define construct candidates, right? So the candidates we said are just true or false. For at each step, we just need to decide whether we just need to try true and false. Basically, try picking the element or try not picking the element. And so to do that, we are just going to say, okay, our candidates are just a list of true and false. And that's all there is to it. And then what will happen is that in this here, would try first add true, and then after that we'll try adding false. Now I said that make and unmake would be empty, but unmake here, since we added a true, once we do the backtrack we need to remove it. And so we shouldn't forget that. So here in our unmake, we would just say A that pop, for example, to remove the last element from the vector, because we added the so because in the make move we added the element, which is basically C. So we would add true and then we backtrack and basically try the rest of the elements, considering that we picked the element. And then after that, remove that true so that we can try the other possibility, which is false, which is not picking the current element. And so pretty much that's all we need to do. We just define these methods that are required by our template, and then we call the template here, which will do the work for us. And so you can see here, this is a very useful way of just thinking about if the problem fits the backtracking requirements, and once it does, just defining these, first deciding how to model it in terms of the solution vector, and then thinking about what the implementation of each of these pluggable methods would be. And that's pretty much all there is to it. So in terms of complexity for this solution, we know that we would have 2 to the power of n subsets, right? And then we know that we are doing DFS with the backtracking, right? And so that means that this is the number of leaves, right? Because this is the number of solutions we need to generate. And then we know that we will do the DFS. And so it's the height of the tree multiplied by the number of leaves. And the height, we can just say at most it would be n. And so n to the power of n. So that will be our complexity here. You can try other examples like generating permutations, combinations with this method. To get used to it. But yeah, this is the gist of it. And yeah, that's it. Thanks for watching and see you next time. Bye.